Today we're going to solve a problem involving pulling a block up a hill with friction. Start by reading the problem statement. A 10 kilogram block is being pulled up a hill. The hill is at an angle of 37 degrees with respect to the horizontal. Let's draw that in. And there's a force of friction between the block and the hill of 40 newtons. If you assume you are pulling horizontal to the hill, let's draw our applied force. How hard do you have to pull to get the block to move? Now initially you might say, oh, I actually have to beat out the force of friction. So my answer is easy, it's 40 newtons. But remember, that's will be the case if there's nothing else acting on your block and it's on the flat ground. In this case, we're on a hill, so it's not as simple as that. So let's draw in the rest of our forces. We have a gravitational force between the block and the earth, pointing straight down. We have our friction force, which is we're going to assume the motion is up the hill. So our friction force would be against motion. And we also have a normal force between the block and the hill, pointing straight out of the hill, not up, but out of the hill. And that's it. So the next step, we would choose a coordinate system. Now, when you're doing hill problems, it's always good to tilt your coordinate system. You want one of your directions, either X or Y, to be in the direction of motion. So in this case, I'm going to choose X. I'm going to choose up the hill as my positive X direction, which means out of the hill would be my positive Y direction. And now the annoying part of this problem is that our normal force, our friction force, and our applied force are in the correct directions. They're either in X or Y, but our gravitational force is not. It's in between X and Y. But that's right, we know how to deal with that. We can break our gravitational force into components. We simply use our vector tools and our knowledge of trigonometry to create our gravitational force in the Y direction and our gravitational force in the X direction, sometimes called Figgy and Figix. And the trick here is to realize that the angle of the hill is the same as the top angle of this triangle that I drew. So our gravitational force in the X direction then would be our total weight times the sine of our hill angle, and our gravitational force in the Y direction would be our total weight times the cosine of the angle of our hill. And we'll figure these out in a second. And once I break my gravitational force into its two components, now all the forces, we have the normal force and the gravitational force in the Y direction. In our Y direction, we have our friction force, our X gravitational force, and our applied force in the X direction. All of our forces are either in X or Y, which means we can now go ahead and start trying to solve this problem. So I'll write a Newton's second law equation for each direction. Sum of the forces in the X, it's going to be our applied force minus our friction force minus the X component of our gravitational force. That equals m times a. And in the Y direction, we have our normal force minus just the Y part of our gravitational force. And that's going to equal 0 because we set up our coordinate system so there is no acceleration in the Y direction. Again, we're looking for how hard we have to pull the block to get it to move. So in the worst case scenario, it's just going to start moving with 0 acceleration. So because how hard to get it to move, we can assume that our acceleration is actually going to be 0. So that's our worst case scenario. The amount of force, the minimum amount of force needed to just get this thing to move, is we can assume the acceleration is so small it's basically 0, and this thing is moving at a constant velocity. So that's one of the assumptions we have to make here. And again, we're looking for our applied force. So if we solve this for our applied force, we get that the applied force we need is equal to the friction force plus the X piece of our gravitational force. Now we already have our friction force. We don't have the X piece of our gravitational force, but we do have another rule we can use. We have our rule that your gravitational force, if we assume this is we can use the local gravitational equation, is equal to m times g. So in this case, it's going to be 10 kilograms times 10 newtons per kilogram if we assume we're on Earth. So this object has a weight of 100 newtons. If we want the x piece of our gravitational force, we can plug this into our physics equation here. So this is just going to be 100 newtons times the sine of 37. Again, the angle 37 should make you happy. We all know the sine of 37 is just 0.6. It's one of those special angles. So this is going to just be 60 newtons. Now I can plug this into my x equation over here, and I can solve this. So my applied force is going to equal my force of friction, which is 40, plus my x piece of gravitational force, which is 60 newtons, and my applied force needed to just get this thing to move is going to be 100 newtons. So there's part A. Now part B asks, if you pull with a force of 150 newtons, what will the acceleration of the block be? So I don't have to go and redo this entire problem. I can use most of what I've done so far. Again, my situation is not going to change. My free body diagram is not going to change. My weight's not going to change. Most of the stuff here is not going to change. The only difference is I can no longer assume that my acceleration is 0 anymore. I'm now given the applied force. I want to solve for the acceleration, so I can still use everything else I have. I'm going to start by writing a new, so this is for part B now. So the sum of the forces in the x direction, still going to be my applied force minus my friction force minus the x piece of my gravitational force equals m times a. I can no longer assume a is 0, but I want to solve for a. So if I divide both sides by m, the m's will cancel out here, and I'm left just with my acceleration. Now I can plug in numbers, do a little math. To save space, I'm just going to kind of write them in up here. So my applied force, it says, is going to be 150 minus my friction force of 40 minus my x piece of gravitational force, which is 60. So I got 150 minus 40 minus 60 divided by the mass is 10. This will give me 50 divided by 10, which equals 5 meters per second squared. So again, a lot of times in these problems, it's a little bit tricky in the beginning because if you have angles, you gotta break something into components to get all of your forces in the x and y direction. But once you do that, you can treat the problem just like a normal Newton's second law problem. And then if you're asked part B's in problems as well, don't try to resolve the whole problem. Look back and see what's changing because you can usually use most of what you've done already.